Good evening, everyone, and welcome to the Vacuum Transport Seminar. This is our 5th edition this semester, and we're very happy to welcome all of you tonight. When I say we, I mean the organizing organizations. So it's Eurotube, Swissloop, the Institute of Hyperloop Technology, Museo Hyperloop, and TUM Hyperloop. And I would like to jump right to our schedule today. So we have 2 talks tonight. The first talk is from the side of Swissloop. It will be Tom Rasek giving the first talk. He's a student, he's a master's student in aeronautical engineering at the Imperial College London. And he will speak about an aerodynamics topic. I will give a shorter introduction in a second. And our second talk will be from Sigrid Jacobs. She's from the side of the Institute of Hyperloop Technology. And she's a product development manager at ArcelorMittal. As a short reminder, we use the tool slido.com. So you can go to the website slido.com, and then after every talk, we will go through the questions that you can put online on this website and have a short interaction around with the speakers. We will put all the details into the chat in a second. All right, so I'd like to jump to a short introduction of Tom. Tom, maybe you can already share your screen if you like. I hope you hear me.
Yeah, hi.
Perfect, hi.
Perfect.
So as I said, Tom is a master's student in aeronautical engineering at the Imperial College London, and he's doing his master thesis in collaboration with ETH Zurich, Swissloop, and the Paul Scherrer Institute in the field of CFD, computational fluid dynamics. And his topic is the aerodynamic shape optimization of a Swissloop pod, and he's an extensive study of shockwave formation and reflection of the Hyperloop tube walls. So his aim of the project is to explore how a shockwave interacts in a finite Hyperloop tunnel at operating high velocities and blockage ratios in order to further develop those systems. Exactly. And okay, so if everything works well, then I will head over to you, and the stage is yours, Tom. Thank you.
Okay, so hi everyone. Thank you, Natalie, for the introduction. So as I said, as Natalie said, I'll be talking about the optimization drag on a Hyperloop pod, especially. So this is quite a new area, a new flow condition that no one's really looked at, which is the Hyperloop pod will have a leading shockwave as it travels even at subsonic speeds. And we expect that shockwave eventually to bounce off the end of the tunnel in some way. And it is yet to be explored exactly what the impact of that is, both on the drag and on the forces on both the tube and the tunnel. So this is a slide that I'll probably run through quite quickly, as I think everyone has a good idea by now, but just the aerodynamic drag for a regular conventional train accounts for 85% of the total resistance at 300 kilometers an hour, which is why we need new solutions to overcome this. And transportation is the single largest emitter of greenhouse gases in Europe right now. And it's also the only sector that has experienced growth in emissions since 2007 and is expected to only continue growing due to growing travel demand. So what is it that a Hyperloop can do better and can improve in that sense on? So travel time is something that can be sped up even compared to conventional rail travel due to quicker ingress and egress times. A really big one is the construction costs for tunnel diameters, which the knock-on effects of which will drive this entire study. Improved energy efficiency compared to conventional rail. However, there are concerns with capacity as well as high dependency on rare earth metals, but the main one, the one that I will talk about today, is the Cantor's limit. So the combination of a high blockage ratio and high speeds will result in essentially supersonic flow around the vehicle, which carries with it a massive drag increase and presents an issue to the structure of the pod and the structure of the tunnel, as you'll have all of a sudden these shock waves bouncing around that will cause stresses you wouldn't see in subsonic travel, or yeah. So just a brief introduction on the Kantrovitz limit. For a given blockage ratio, there exists a pod speed that causes choke flow in the constricted cross-section between the pod and the tunnel wall. So if you want to think of the pod in a slightly different way, you can think of the pod as almost like a nozzle or a venturi tube, but a venturi tube where eventually the flow between the tunnel and the pod becomes choked, and suddenly you have supersonic flow because you can't carry that mass of air through a much narrower opening between the pod and the tube. Sorry, the pod and the tube than just through the tube itself. So as you can see here, you've got a much larger cross-sectional area of the tunnel that is suddenly getting constricted. And as you'll see on the graph on the right, the Kantrovitz limit is sort of well, that's the blue line there. And what we're trying to do is operate well beyond it. So that red line there is the conditions that you would expect in alpha tube. And just for a little bit of an illustration, that little blue dot there is where conventional rails is right now. So this is why sort of these effects that we're looking at are not a problem for conventional trains. But once you get into the higher Mach numbers, or once you get into lower blockage ratios, you start hitting these problems. And why do we want to hit higher blockage ratios? Is the cost of tunneling is essentially proportional to the tunnel cross-sectional area from data that we have from building the Gotthard and from building tunnels under the Alps in Switzerland. So we know that if we can suddenly half the diameter of the tunnel, half the cross-sectional area of the tunnel, we can achieve a 50% cost saving. And I don't think I need to explain why we need to go higher speed as well. So the problem definition: choke flow results in leading shockwave forming in front of the pod. So essentially the flow cannot get away from the pod, or cannot pass through the pod to the end of the tunnel quickly enough. So you get an accumulation of pressure in front of the pod, and this manifests itself as a shockwave. And this shockwave was found to result in an average power increase of 49% and a peak power increase of 230%. And that is compared to a conventional tunnel. So all of a sudden, not only are you spending more power, but your peak power, which will hit you actually at the moment that reflected shockwave that we're going to talk about hits the train, is going to cause a massive deceleration of the train unless your train is suddenly way more powerful. We also looked at the impact of the trailing shockwaves. So as you'll see the flow structures in some later images, there's some shockwaves behind the train that form as well. And those actually just dissipate when you decelerate. So they were found not to be concerned. So the aims of this project were to study the existing models and methods for simulating transonic flow in tunnels, to quantify the loads on the tube caused by a reflected shockwave, and investigate strategies to mitigate the strength of the reflected waves. So as we've sort of very briefly established based on some literature, the drag increase is quite significant, but there will be ways that we can mitigate that. Secondary objectives are to develop an optimal tunnel geometry to limit the strength of reflected waves. So that's one of the mitigation strategies that I talked about, and define a safe operational envelope of the system given maximum loading of the pod and the tube. So here are some examples of ways that we're trying to mitigate this effect. So in essence, in order to reduce the wave drag that we're experiencing, what we need to do is smear or dissipate that shockwave into a series of weaker shockwaves. And not only is this going to result in a smaller drag increase, it's also going to make a night and day difference for the comfort of the passengers, which, you know, would by default experience this almost impact or crash when that shockwave hit the pod And all of a sudden, you know, with the, especially with mitigation, with the power control of the train as well, we would allow them to basically not feel anything. And so a couple methods that we've tried at the end of the tunnel here are sound absorbing panels. So this is just inspired by industrial design, where in essence, we're just dealing with another kind of shockwave and we're trying to dissipate it. And what they do in offices and in recording studios is dissipate it using sound absorbing panels, which dissipate a sound wave into a variety of different directions, causing it to not really be as concentrated and in places sort of destructively interact with each other. Another suggestion that we found from literature was this thing called log spiral geometry, which in essence causes the shockwave to do the exact opposite thing, which is collapse onto itself. Now, why would we want to do that is that this method was found to actually delay the reflection of the shockwave. So another strategy, if you can't have that shockwave be weaker, is have that shockwave hit the train much later in its journey. So for instance, once it's slowing down, the sort of additional deceleration is not that big of a deal because we have A, some power overhead, and B, we really kind of are decelerating at that point. So on the right, you just see a few equations for the log spiral geometry. It's essentially a geometry that's specific to a certain Mach number, and that Mach number comes from the wave. So that's something that we had to simulate from in CFD to find the leading shockwave propagation speed. And again, I'll show you that in an illustration a bit later. So these are just the tunnel geometry's final meshes that we came up with. The acoustic mesh had to be modified a little bit because what you saw in that previous GIF with the office space is us dealing in sort of a 3D space. And even though a tunnel is a 3D area, it's a wave moving essentially just in 1D back and forth. And if we just try to reflect in different directions, it's likely going to coalesce back into one coherent wave that again hits the pod in the same way. So what we've tried to do here is actually delay the reflection on parts of the flow, but not delay it on others. So as you can see, the sort of bottom part of the wave will reflect a bit later than the top part of the wave. These are all axisymmetric meshes. So if you will, just try to reflect them about the x-axis for yourself. So yeah, they will essentially form a more continuous pattern than they do here. Another method that's been suggested in literature is pressure relief ducts. So in essence, this would involve connecting the two tunnels at the ends. So as you think of a train approaching the end of a tunnel, the pressure is going to build because it has nowhere to go. So all we're doing here is actually giving it somewhere to go, which is the other tunnel. And fortunately, there has been some research done on whether this would negatively impact another train passing through that tunnel. And it was found that even if there's two trains passing each other, there is still a really nice drag reduction in this. So that's that blue line there, which is drag in a closed tunnel, a Hyperloop tunnel without pressure relief, with and without pressure relief ducts. And you can see that even with another train passing, we still see a much more sort of consistent, less peaky increase. So that top line that isn't red, that is a non-Hyperloop train, if you will, a train running at atmospheric pressure. And what you'll see there is that even without any sort of mitigation strategy, the Hyperloop train actually reaches a higher peak power, despite having a much lower pressure to work with. We did some validation cases to make sure that our setup made sense. The first one was simulating an experiment done by NASA in the 50s with a bullet in a wind tunnel. And this was just because it was a very similar sort of environment to what we have with the Hyperloop pod, actually, with reflected shock waves and oblique shock waves in front of the bullet as well. And we found that the K-omega SST turbulence model was a little bit better for us here. It tracked the results a little bit more accurately. We also did some transient simulations here because our final simulation is transient. But then the main validation case that we did was using another paper that was recently published with an overset mesh, which is essentially a method of having two meshes on top of each other. One is the tunnel mesh and one is the pod mesh. There are other approaches, but the advantage of this one is that we can actually just create a pod mesh and then swap out tunnels as we go and iterate really nicely without actually having to redo the experimental setup or being worried that we screwed something up while changing the geometry. And we did a comparison of both methods against the paper, and we were within a few percent, as you see in that table there. And actually the results in the end are about 1%, not 7%, because these were done with quite low resolution meshes. And this is finally the flow around the pod. So this is, these are contours of axial velocity and density as of our validation case, essentially. And what I'd like to bring your attention to is those trailing Mach patterns that actually occur behind the pod. And I'll show you something interesting in a bit, is that we found that that pattern really changes quite dramatically with the blockage ratio, but also it dissipates very quickly on deceleration. So it's this sort of scary rocket engine-like pattern, but it doesn't have too much of an impact on the pod. What does have a big impact on the pod is what you see in front of it, is the pressure, and there's the pressure buildup, and in this case, density buildup that you see. So this is, as I said, the variation with the blockage ratio. So the blockage ratio, as I explained, was the area ratio of the tunnel to the pod. And actually, Alpha Tube is quite ambitious in its design in that sense, in that it is aiming for quite a high blockage ratio. Now, what this allows is a large train area, train volume, relative to the tunnel. So in essence, you can, for carrying the same amount of passengers, you need a much smaller tunnel. And that, as we talked about, results in cost savings. But it results in quite a different pattern in the flow as well. So all of a sudden, that crazy shock pattern that we see changes into something that is more like this. And it's quite counterintuitive, because we found in literature that that pattern that we're seeing here in this slide is actually more like a lower speed pattern, which is more interesting because we're further away from the Kantrovitz limit. This is a picture of essentially the same pod, but after the leading shockwave has impacted the tunnel end. So what you see is that the flow actually looks similar, but if we look at the axial velocity numbers between this one and this one, you can all of a sudden see that the flow is more intense in it, essentially. It's the same flow, but the pressure is approximately doubled and the peak velocity is increased by approximately 50%. And that small image that you see below, that is the sort of remaining third of the domain. You can see a very, very small pod, sort of 60% through, and then you see a compressed region, which is essentially a reflected shockwave that has hit the end of the tunnel and then is now hitting back the pod. And while it doesn't change the flow structure from a velocity perspective, it massively, massively changes the drag on the vehicle, which I have here. So this is our vehicle traveling through Alpha Tube, and between sort of 3 and 8 seconds, it's holding constant speed. You can see the drag still going up, which is partially due to the pressure buildup and partially because the pod is just accelerated. So you can just about see that at 3 seconds, the drag has just gone up, the pod has accelerated to its cruise speed, and the drag is very slowly going up. And then at about 8.3 seconds, we see a massive drag increase, and this is that reflected shockwave hitting the pod. And it doesn't recover from then on. So you have actually a further increase in drag, but more importantly, a really sudden increase in drag that the passengers would definitely feel, and that, the pod's induction motors wouldn't be able to counter. So you would all of a sudden get quite a significant deceleration, which is why that the patterns that we're looking at the end of the tunnel are quite significant, because if you get this in cruise, then all of a sudden you will have lost quite a lot of speed. And if you get that in the middle of your journey between Basel and Paris, and you all of a sudden can only go a half, maybe a quarter of the speed that you could before, then you have a big problem. But if that happens on deceleration and you can manage it, then we're dealing with something that's much more manageable. Yeah, thank you.
Thank you very much, Tom, for the interesting insight into your master thesis. Thank you very much. I would say we jump right to the questions of the audience in the Slido tool. Yes, there are the audience has quite a lot of questions. So I will start right away with the first one. And the question is, how would the shock wave and the pressure distribution affect the aerodynamics of two vehicles following each other? Have you looked into it?
So that's not actually something that we've looked into, but it is something that prior research with Swissloop has looked into. So I can definitely refer you to that paper, but no, we haven't looked into that ourselves.
Exactly, all right. Then second question, what is the optimal blockage ratio for 1 millibar regarding the shock waves?
The optimum blockage ratio regarding the shock waves. Well, if you were to look at just the blockage ratio, then the optimum blockage ratio would be anything below the Kantrowitz limit. But I suppose it's a compromise between making an attractive system that people want to use, whether it's due to travel time or due to costs, and one that is sort of feasible from an engineering perspective. And again, cost plays a role there, but in a different way. So it's more of a, it's not just an aerodynamics problem in that sense.
Yes, right. Then somebody wants to know, can you use innovative materials on the pod to mitigate leading shock waves?
Innovative materials is something that is being researched a little bit, and I'm aware of some research that is using porous materials to mitigate the shock waves. So that is doing a little bit of the same as we are doing, but we're trying to break down the shock wave at the end of the tunnel. And I know there's some research being done on breaking down the shock wave that is just behind the pod. So can you still see my screen, Natalie?
Yes, we see.
Okay. So there is some research being done on breaking down the shock wave at the trailing edge of that pod, which again would help drag. But what I've seen as more popular is the research being done in innovative shapes of the pod, because what we're seeing here with that expansion wave at the end of the pod is, well, our pod is just two hemispheres connected with a cylinder, and the ideal pod shape would be more likely something that looks a bit like the inside of a rocket engine. So there's been some research done into sort of finding the optimal pod shape as well, and that might be a bit more significant, I think.
Okay, then the next question. Have you been able to derive a chart to describe the optimal ratio between blockage ratio, then in brackets function of diameter, and pressure for Hyperloop applications?
Of blockage ratio and pressure. I'm not sure about that. What we have found is that the flow behavior, and I guess this isn't the first question of the series that kind of touches on pressure, but we've actually found that the flow structures that you see here are quite independent of pressure. So if we were to run this simulation that you're looking at in front of us, for example, so this was run for, I believe, 1/100th of an atmosphere. If we were to run the same simulation, but for 1 atmosphere, we would be looking at the exact same flow structures, just with much, much higher magnitudes. I don't know if that answers the question, but yeah, pressure is fairly independent in that it is just a scaling factor in all this.
Maybe the question was also related then to the force, I guess. I mean, so what you just said is that the flow field, or like the field that behaves in the same way, but it's just the magnitude changes, right? Yeah. Maybe the question was meant in a way, if then that change of magnitude somehow maps to an ideal pressure in the tube, if there's like an optimum somewhere.
I'm not sure I could say. Yeah, it's a bit, I don't feel it's necessarily an optimization problem, because again, you're sort of, I think it's something that I am going to touch on in the final report, but the problem will be more along the lines of what are our material requirements, and therefore what is the highest force that we can afford. not sure I would say there's an optimal force, if that makes sense. I hope I'm understanding the question right.
Yes, no, I see, yes. Okay, then somebody would like to know what have been your boundary conditions to conduct your CFD simulations?
So at the start, so for these validation cases, we had outlet pressure boundary conditions on both the front and the back, and then moved the pod mesh. And then on these final ones where we're actually trying to simulate alpha tube, we have a wall at the end, no slip wall at the top, access to the bottom, of course. And at the end, we have again a pressure outlet, which obviously is not really physically an outlet, but it's just there to impose the given pressure that we have in the tunnel.
Nice. Then somebody would like to know, have you performed any shape optimization on the pod to identify an ideal shape? If so, what solver did you use and what are the improvement signification?
No, we didn't do any shape optimization. It's a good question, and it's something that's definitely interesting. And like I said, I'm aware of some research, I think at Delft, where they did do just that, but we didn't do any shape optimization.
Then somebody would like to know, did you compare the shock speed with the piston analogy?
Yes, it's something that I'm working on a derivation of sort of my own math of that, but sort of going by literature, we did find that it is quite close. Actually, our theoretical calculations based for this log spiral shape are based on theoretical sort of piston effect calculations, where we found that the shock speed that we were expecting, the leading shock wave speed that we were expecting, was about 400 meters per second. And then I'm not sure if I have it. I don't have it in. I do have it in the table. No, I don't. But the actual values that we found in the end were 442. So it is a valid method, and it is a good starting point actually to go with.
All right. Then somebody would like to know, what solver are you using?
So we're using ANSYS Fluent 2021, and as I said, K Omega SSD. We did consider using DES as well, but it wasn't really worth it for our applications because we're just looking at the buildup of pressure, and it would have changed the mesh approach that we're able to use.
Very good. And then second last question, what does the temperature in front and after the vehicle, or what does it do? Does thermodynamic effects, for instance, compression, has impacts on the flow?
Yes, there's quite a large increase in temperature. I actually have that in front of me, so I'll be able to tell you exactly. So there's about a 200°C increase in the air temperature in front of the pod, but we're going to talk about a little bit about the heat transfer in the final report, and we don't think it's as big of a factor on the tube itself because the heat transfer between really low pressure air and concrete is going to be really small, but it will be a design consideration for the leading edge of the pod.
Great. Okay, then the last question, somebody wants to know, why is the optimal pod shape more like a rocket engine?
Why is it more like a rocket engine? Because, so that's actually for the trailing edge of the pod. For the leading edge of the pod, literature suggests that you might as well go with a completely blunt edge. But why did I say rocket engine for the trailing edge of the pod is because you want to expand that flow that's essentially at Mach 1. It's the exact same speed that you would have in a rocket. It's just stroke flow. You want to expand that as efficiently as possible to sort of atmospheric conditions. They're not really atmospheric, but they're atmospheric for the tunnel. And actually, okay, if you think about it, it's kind of an inverted rocket engine. So because, well, it's not a rocket, but the rocket is the surrounding tunnel, if that makes sense.
Yes, yes. Okay, so those are all questions. Thank you very much, Tom, for your participation and your insights to your master thesis.
Thanks a lot for inviting me.
Thank you very much. And it was really interesting to learn about it. Thank you very much. Yes, so we would like to hand over now to the next speaker, which is Mrs. Sigrid Jacobs. And I would like to hand over to Lukas from the Institute of Hyperloop Technology to give a short insight about her. Thank you very much.
Yeah. Hi, Sigrid Jakob. Thanks for being here. I just wanted to give a little bit of an introduction to you. So you're working in global research and development at ArcelorMittal, and you're working as a product development manager of electrical steels at ArcelorMittal. You've recently published a paper, which I liked a lot, which I've read, Electromagnetic Materials Suited for Electrified Transport. You elaborated on some material properties, simulations of systems used in the transport system of Hyperloop, or such as Hyperloop. So we're excited to learn about all the things from a steel manufacturer's point of view on propulsion, braking, guidance, all especially for Hyperloop. Thank you for being here, and the stage is yours.
Okay, thank you. So I'll start sharing my screen. And I think this is the one I want, right? Right, so we are going to present something about the electromagnetic system designs that we've made for Hyperloop. This is work I've done with my colleague Jan Rens, but I'm just presenting on my own now. And we have done different aspects of the calculations. For today, I've just put some work on the tube side, the propulsion and the levitation, so braking is not going to be covered today. The first part is the introduction. Everybody knows about sustainability, so I'll just quickly repeat it about electrification that needs to take place and that the internal combustion engines for cars are going to be phased out. That it also means that we don't want the new systems to have critical raw materials, that the reliance on neodymium in permanent magnets, the fact that it is linked to single sourcing or mainly single sourcing from China, but also the fact that there are pricing issues about these materials mean that in the next aspects of the presentations, we've mostly worked on machines that do not have permanent magnets in it, and certainly not neodymium iron boron magnets. This was the previous slide was a view from Europe. This one is the view from the United States, but the problems are similar. We have in ArcelorMittal a will to go to carbon neutral steels. This is the business plan behind it. But the electrical steel business has been since a long time working on renewable electricity projects and high power density machines for electric cars. So making a step over to Hyperloop was nothing that new for us, because it's part of our philosophy on green steel and green applications. So on Hyperloop, we know that there is a problem in terms of green cargo transport. It's difficult for ships, it's difficult for planes, and it is also difficult on land. And that is all linked to the battery challenges that still exist today. And of course, there are hybrid powertrains being developed with hydrogen combustion, but green hydrogen is also nothing really available today. So that's why we are working within the Hyperloop technologies, and we're also part of the GTC20 working group in the sense and standardization effort. So now let me come to the technical aspects. So we are taking a look at all the different materials that are being used in Hyperloop systems. We have ferromagnetic materials that are really used inside of the machines. But we also need to assure that the mechanical properties are okay, because there are high forces in such a system with pulses, as was just described in the previous presentation. And so there need to be a clear view on the mechanical aspects as well. The next problem with Hyperloop is definitely the thermal balances with the vacuum or the near vacuum. It's difficult to cool the system, so we also have to take care about the thermal conductivity of the materials that are being used. And so we are mainly focusing on the machine designs and also on the integration of these machines inside of a tube structure. The structural analysis that is shown here is looking when you have a propulsion system as it is shown here in terms of the stator and the mover, how this can be fixed to this kind of circular structure with the necessary stiffness and the necessary bolted connections that assure that the tolerances between the stator and the mover still can be respected. And that is not an easy task. The forces that are mentioned here will be explained later on when I talk a little bit more about the propulsion machine. So there are different kinds of bolted connections. I first discussed these ones, but we also have to assure that from the top to the bottom, so to assemble the stack as such, there also needs to be a stiff connection that resists also slipping out of the fixation system in the back. And that is all done with Eurocode calculations, but we go further also in terms of the structural analysis. I just wanted to give a brief overview. This is here regarding the bolted connections on the back side. And it's also explaining why we have worked with these plates every 500 millimeters and why we are working with a combination of systems that are stiffeners and that are also products on the longitudinal side along the tube. So we need these bolted connections, and we also need to assure that when we propose integration structures that it's possible to make them. So when we have made designs, we assure that it's also possible to assemble it, to put it on the required preload. So it's more than just proposing the materials, it's also checking that this can be assembled on site. Right, now a little bit more of the electromagnetic work. We have worked on linear synchronous motors, as I said, because we don't really like working with permanent magnets. We have used in this design 2 round field linear synchronous motors. They are put on either side of the vehicle, and that is done to cancel out the forces between the stator and the mover, because the forces are very high if you make it unilaterally. There are different magnetic units. They all have laminated yokes, and these are arranged in order to have a propulsion force of 110 kilonewtons for a maximum speed, as we all know. And this is first of all calculated by using laminated solutions in 0.65 millimeter thickness and basic carbon steel for the outside. And that is done just to see how fast this leads to the increase of losses in the system and therefore reduction of the efficiency of the system. So first of all, we've been doing 2D modeling. We always use JMAC because we like the way it allows to do post-processing for the loss calculations. And it also allows to work with very complicated models in a fairly fast way. The flux distribution is shown here. The data we use as input is measured in-house for the electrical resistivity, the magnetic permeability, and sometimes we work with the reduction of the size of the model in order to be able to have sufficiently fast calculation times to do a lot of iteration and identify what the best possible integration system is. In this case, we have the stator laminations. You see them here in a 2D view. You have a back plate beside or behind these laminations, which is then used to act as a stator housing and also to connect these ribs that are taking it into the tube connection. The point of the first analysis was to check where do we put these ribs? Do we put them behind the tooth or do we put them behind the slot? And it's clear from these flux distributions that you can see that based on the intensity of the fields that go into the back plate, that it is better to put the rib behind a tooth. And this is then what we have done for the rest of the analysis in terms of the force calculations and the loss calculations. The skin effect is something which is interesting because the higher you go in speed, this is, in fact, I didn't put it here on the slide, but this is at maximum speed. The more you go towards maximum speed, the more you get skin effect. And so in fact, you get shielding, and therefore the fluxes don't go as much as they did at lower speeds into the stator housing. So that is in fact a positive effect in this case. The 3D modeling is the next step. You then can see these ribs, you have the stator housing, you have here the stator yoke, all the laminations behind each other, but they're not drawn individually, and here are the conductors. And you can see that, first of all, the 2D and 3D modeling give very similar results. And also the skin effect is clearly to be noticed. So when the speed goes up, we have an increase in the flux density, but we also have a change here in the behavior inside of the laminations and also towards the housing. If we look at the losses, then we do see a difference in the results of the 2D and the 3D modeling. So first of all, you can see that the difference in losses is mainly on the aspect of the stator housing, and it is mainly also visible at the different speeds. So when you go at low speed, you see here, first of all, in 2D, a fairly low drag force, but in 3D, it is much higher because we have these additional components that you get because of the end effects that you can include in the 3D model, but which you can't include in the 2D model. And accordingly, then the drag force associated with these losses is going to be also fairly different. So it is always important that we make the additional calculations to assure that we're giving the right predictions in terms of the materials to be used. If you look at the total electromagnetic loss analysis, you see that in this choice of motor solution, the copper loss is in fact not as important as the total steel loss. Very often you get situations where there is so much current being pushed through that you do have a predominance of the copper losses, but it's not the case in the configuration we chose here. It's really, as said before, it's the stator that is really creating the problem in terms of the efficiency of the solution. The eddy current losses is done in a separate way in a 3D lamella. So you take one lamella out of the stack and you calculate there in a 3D way the eddy currents, and you can see here clearly that within the lamination there is a skin effect happening. And so if we take in comparison with this table here, that was 2D, then you see the losses that are generated in the as eddy current effect in the lamella, but you can see with the 3D calculation that it is even higher. So this means that the iron losses are still higher in reality than what is said here. So if we bring this all together, we have the problem of the high stator losses because the electrical steel that was chosen is too thick. And we see that for higher speeds, it's not acceptable anymore to use this very basic material because it would start reducing the efficiency substantially. But you can reach good efficiencies if you go over to better materials. Now, a quick word regarding the levitation. For the levitations, we've used a wound field electromagnet. So you can find papers where this sort of solution is used. You have like a system that is attached to the roof, possibly, where you have a excitation coil, and it is around the mover, so attached to the vehicle. And then you create, in fact, an induction effect against the solid rail. But what happens when you do this at the high speeds that we're talking about now is that you get too much eddy currents circulating. And therefore, we've proposed a solution where you have a laminated stator yoke that counteract these effects, but you still work with an excitation coil on the pod side. Then we've gone into the modeling of the solution. We've seen that the flux densities can be fairly high here, especially in the corners of these electromagnets. And when we go through 3D modeling, you see again that the fact of going through this stator part, which has a laminated solution, is much better in terms of intensity of the fluxes and the associated currents that will be flowing. So the levitation simulations see that we can get this very strong reduction in losses thanks to a laminated solution. And I think I've said most of what is already on this slide, and that is definitely not possible for Hyperloop to work on such a solid stator as it sometimes is done in magnetic levitation trains at low speeds. And this is in fact a little bit of the basic work regarding the modeling of the losses. So what you get is that in fact when a pod is passing by, there is a pulse flux that is generated inside of this rail system, and that means that you have non-sinusoidal effect. It's like a strong DC bias step that is applied onto the stator laminations, and therefore when you calculate the losses, you can't use a classic loss equations as is normally done with Bertotti, where you split up between hysteresis, eddy current, and excess losses. We work with a Price-Sag model for the hysteresis losses, and then we have another method to calculate the classical losses, but to include the skin effect during the calculations of the fields before we go into the post-processing, and that then generates the total losses the way we can provide it and then use it in the efficiency calculations. But I didn't put the detail of those calculations in these slides because I thought it would lead me too far. So I tried to go quickly through all the sort of work we're doing and give you an overview of the sort of modeling we have for a propulsion system and also for a suspension or a levitation system, that we are careful to do the 2D, 3D work whilst integrating the mechanical systems that are needed to fix everything to its surroundings, and that we try to go into very much detail in order to give the best possible evaluation for the losses that will occur, the drag effect they will create, and hence the efficiency loss that they will generate. And that is in fact what I wanted to present in a nutshell today. So thank you.
Thank you very much for your great talk. I've learned a lot. I've got so many questions left, but I've seen that there have also been popping up a lot of questions from the audience. So we'll try to get through them quickly, or we'll take all the time we need because we have some. How are the plates every 500 millimeters, the ones on the tube, attached to the tube? Is heat transfer an issue?
Yeah, sorry, I think the cleaning lady is outside my office now. I can't hear you.
That's all fine. We don't hear it.
Yeah, okay, but you were asking about the heat transfer, right?
Yeah, so the plates are attached every 500 millimeters
Yes.
to the tube. Is that an issue for heat transfer, and how are they attached? Are they welded? Are they?
Yes, so the connection here is indeed welded, and the idea was to make these ribs as small as possible, so they are as big as they need to be at the position of the propulsion system, but you can see that they become thinner as you go further down. And the point is definitely that you should not have these ribs all over the tube in a very substantial way, because then definitely you will disturb the airflow, and you will have a problem in the heat evacuation. But the losses that we are calculating here in this system are meant to be reduced further down by going to thinner steel grades with better properties. So in a way that the heat that would be going into these ribs by conduction would not be of such a nature that they start creating a deformation of the the tube. In fact, we get more deformation effects because of the sun shining than with the solutions we have so far because of these connections.
Interesting. Yeah, I would also like, maybe we can ask our aerodynamics guys at the end, but maybe it's an idea to close them up to not have these aerodynamically disturbing shapes there. So the second question is, why have you decided for the suspended levitation track on the top?
It wasn't really the idea that it has to be suspended. I've called it like that because it's a common word to use. I think it's wherever you put it, you could put this system, turn it 90 degrees and use it as a sideways guidance system. It was more meant to explain the principles of the work. You see this kind of system which have permanent magnets or a combination of permanent magnets with excitation coils. But the focus of the talk was mainly to say that we think you need to make the interaction of the part which is connected to the pod and the part which is connected to the tube. You need to make this partly in a laminated way. And that was basically the message I wanted to send out.
So yeah, but you haven't focused on any levitation that is focused on electrodynamic levitation, for example, right?
No, it's always electromagnetic suspension systems that we're using. Electrodynamic systems, basically, very often they work with aluminium as a reaction, and we are a steel supplier, so you can imagine we're not very much into that topic.
Yeah, okay, I think that perfectly answers the question. Then there's, how far have you looked into the cooling of your electromagnetic components? Is this a decisive factor for the studies conducted?
Could you repeat that? Which effect?
Oh, sorry. Yeah. How far have you looked into the cooling of your electromagnetic components? And is this a decisive factor in the studies you have conducted?
Yeah, we haven't really gone into the cooling yet. We first wanted to make different proposals that have the best possible efficiency so that it wouldn't really be so important to cool at least the laminations on the steel types that are being used. I think the cooling will be, in the end, it will be more important for the power supply, and it will be, I think, more important on the pod side, but not critical within the tube, at least not on our side, which is the status of the propulsion and the guidance or the levitation systems.
Okay. So the next question is, which assumptions are your losses based on? Which vehicle weight, which interaction length of the propulsion system? So what's your basic assumptions there?
Yeah, it's basically this one. Yeah, maybe I haven't written it all completely clearly. So we had derived from the white paper from Elon Musk what sort of forces we would need based on the dimensions of the pods that were mentioned in there, and then came up with this 110 kilonewton. But it's true that in the papers we've written, it's better explained than here on these slides, where it's a little bit too compact. And I don't know the numbers by heart anymore now.
Yeah, we'll definitely have a look into that. I'm also not sure what the numbers in there were. Mm-hmm. But 110 kilonewtons doesn't seem to be that much. So it's a low propulsive force, right? It's low G force, maybe 1 per second squared. So
I really don't remember exactly anymore. It's a while since we did these calculations.
We'll have a look at the paper. I already posted it in the chat, the paper, because somebody asked also that question. So the paper is down in the chat here.
Yeah, there will be papers coming with. We did a presentation also on the SMM conference, which was 2 weeks ago in Grenoble, and in EEMODS, which was in Frankfurt 1 week ago. So there's 2 more papers coming up. Then you will have more details in those papers. Yeah.
Well, you are busy. We are definitely having a look out for those papers. There's some questions. How do you feed through the power cables into your vacuum environment? Flanges and steel, have you looked into concepts for those? You probably haven't, because you're more into the electric steel, right? Not into the tube steels.
That's it. The only thing we do in the, where is it? I think here in the structure, we haven't shown this here, but there are, the conductors are here, and then through the bottom, in fact, there are then like cable guides and systems that allow the power supply to be conducted throughout the tube. So that's basically on the bottom side, which is not shown in this image. Okay. But it's not our focal point. We just integrate what we think is needed in terms of the diameter of the conductors, and that's it.
So then there's one more question on the simulations. Why are there such a high difference between simulations of 2D and 3D? You've said that there's like a 2x difference at some point in time.
Yeah, the difference between 2D and 3D is on the one hand side, and I browsed through that too quickly, is that there are a lot of stray fields, so there are the ones that go into the steel structure. But when you work with the 2D calculation, as we did it here, you have like an endless stack of electrical steel that goes on forever. And then there was also the end plate that goes on forever. When we go into the 3D calculations, we have also taken into account that there is a parasitic air gap between limited lengths of stacks that are interconnected. And you need a few millimeters of air in between these stacks in order to be able to make the system into the tube. And this creates then, in fact, additional end effects here at the beginning and at the end of the stacks of the steel. And that is also a difference between the 2D and the 3D calculations.
Oh, okay, yeah. Otherwise, you would also have a problem in difference in length for warm and cold materials. Yeah, of course. Okay, 3D simulations it is. How do you connect the cabling for the linear induction motor between the outside and the inside environment? Okay, we kind of have that already. What's the power used for the shown propulsion system? I've also had 110 kilonewtons, but
yeah, it's also in the paper. I don't really have the details. It's just different frequencies that were used in order to simulate the different speeds. Sinusoidal. I don't think we put harmonics on it, but yeah, sorry, I forgot about those elements.
Yeah. So we'll see about the power requirements. Do you know maybe a little bit about how much power you need per kilonewton kind of? Is that kind of a factor that exists?
No, I didn't check that neither. It's all good questions. I'm noting them, and the next time we write the paper, I will make it clearer. Sorry about that. Well,
we have students with a lot of questions, so here we go. Did you calculate the drag force for a 30-ton? Okay, we also had that kind of 30-ton Hyperloop vehicle. How much will it be compared to the propulsion force? So what's the drag force in comparison to the propulsion force? How much percentage of that is that?
It's true. Here it is 100 kilonewton is the propulsion force, and the drag force calculated here is here. So it's like 5 compared to 110. That's the proportion. That's the drag force created due to the losses in the electromagnetic systems.
Yeah, okay, so 4 to 5%.
Yeah.
Okay, interesting. What's the optimal size for the levitation core of the levitation system? The length of the levitation core?
So the length on the stator side is obviously as long as the tube is. So this is like an endless but interrupted tube. And then here it depends on the force that you want to apply. Usually this is done with different short segments because it's all with these coils around it. I'm not quite sure I got the detail of the rest of the question.
So I think it's the magnetic core that is here now 400 millimeters. So what's the best length? Is it shorter or longer?
It's just done like this because it's practical to make it in 400 millimeters. And then you put different units behind each other in case you want to create more force in order to hold up a more heavy vehicle or if you have different requirements. It was just the practical size to make these cores.
Okay.
We have used different kinds of materials. This is being done with iron silicon materials. It can be done with iron cobalt materials, and some of them have limited supply dimensions. It was just for a practical reason.
Okay, interesting. So I think that's all of the questions finally. Thank you very much for your answers and your insights. I will hand over to Nathalie to give you a quick look at what's up next week.
Thank you very much, everyone. Thank you, Lucas, for the questions. And thank you again, Sigrid Jacobs, for your talk. It was very interesting. And again, also thank you to Tom Rasek from the Imperial College London for his first talk today. And of course, also thank you to the audience and the organizers for participating today and for tuning in. So as mentioned right at the beginning, it was our 5th edition today, which is the second last edition this semester. And in a week, next Monday at 6 p.m., we will have our last seminar of this semester. And we will then learn about it's not loading. We will learn about a parameter study on the effect of viscous boundary layers of a tube design, which comes from the side of the Institute of Hyperloop Technology. And also we will learn about the aspects of polymer-based brake pads for linear braking, which is coming from the side of the Eurotube Foundation. Exactly. So until then, we wish you a great evening and a great week. And we would be very happy to welcome you again next week for our last session of the seminar, and we'll be pleased to welcome you again. And until then, we wish you a great week and a good evening. Have a good night. Good evening.
Thank you very much. Thanks,
Thank you very much.
Bye. Have a good night.
Have a good night.